ก็เช่นเคยนะครับพอดีมีเพื่อนถา
From
มมา
energy
นะครับเกี่ยวกั
conservation,
บ
the
ซูม
total
ว่า
temperature
อยากบางทีสัมภาษณ์กันแล้วเนี่ยอยากจะเอา
at point 1 is
ไปอ
equal
อก
to
ไลฟ์ Facebook ตอน
the
สัมภาษณ์ด้วยนะครับ
temperature
เป็น
at
สัมภาษณ์
point
ผ่าน
1
ซูมเราจะ
plus
ไลฟ์
the
Facebook ก็
velocity
ไล
of
ฟ์
the
ด้วย OBS
gas
นะครับจะเป็น
squared
โปรแกรมฟรีที่ผม
plus
เคยสอนไปจริงๆโปรแกรมซูมเนี่ยมันก็ไลฟ์ได้นะครับแต่มันต้องเป็นเวอร์ชันโปรเนื่องจากผมก็ไม่ได้ใช้เวอร์ชันโปรนะครับจริงทุกวันที่โหลดซูมมาเล่นก็ยังไม่เคยไปมิทติ้งกับใครเลยนะครับเขาถามมาว่าเขามีปัญหาว่าก็คือมันภาพไม่ออกทำยังไงนะครับอันแรกนะครับต้องจำไว้ก็คือตัวกล้องเนี่ยมันไม่สามารถรันพร้อมกัน2โปรแกรมได้นะครับเวลาจะใช้อย่างเงี้ยคุณต้องเปิดโปรแกรมซูมขึ้นมาก่อนนะครับก่อนที่จะเปิด OBS ถ้าคุณคอนเนคกล้องไว้แล้วคุณไปเปิด OBS แล้วเปิดซูมปุ๊บเนี่ยมันจะไม่เจอกล้องนะครับแล้วต้องเปิดซูมก่อนแล้วค่อยเปิด OBS นะครับจะเปิดซูมเสร็จนะครับอันนี้ผมก็มาเข้าวิดีโอนะครับแต่ไม่ได้มิทติ้งจริงนะครับแล้วก็มาที่ OBS นะครับในตัว OBS นะครับเราก็เลือกตรงซีนครับบวกเข้ามาเพิ่มซีนเข้ามานะครับอยู่ตรงนี้ก่อนนะครับเพิ่มนะครับจะดีที่สุดนะครับวิดีโอที่ใช้เป็น Windows มาเรียบร้อยแล้วก็ถ้ามีปัญหาก็มีอีกทริคนึงก็คือเลือกที่เป็น Display นะครับ Display Capture แต่ Display เนี่ยมันก็จะเหมือนกับเอาทั้งหน้าจอมาหมดเลยนะครับก็คือถ้าใช้เงี้ยปุ๊บเนี่ยนะครับผมเลือกอันใหม่ให้ดูนะครับอีกอันนึงเดี๋ยวผมจะเอาเป็น Display นะครับผมก็เลือกมาปุ๊บเป็น Display Capture โอเคไปนะครับแป๊บนึงครับคือเลือกตรงนี้นะครับให้เลือกนะครับ
in the direction of the axis, right? The turbine is spinning along an axis and the flow moves along the axis. So we have an axial turbine, right? So you can see here you got your combustion chamber, the hot gas is coming out. You can see the compressor consists of many stages. The turbine here is only about 3 stages. So the number of stages in a turbine is less than that of a compressor. There's not just axial turbines, there's also radial turbines where the flow enters in the radial direction and then kind of leaves in the axial direction. So here this is an example of a radial turbine, a little turbocharger there. Okay, in terms of the sort of the velocity of the gases moving through the turbine, we use the same terminology as before. So the velocity of the gas is given the letter V. The axial component is given the letter Ca, and then the relative velocity between the gas and the spinning blade of the turbine is given the letter W, big W. Okay, so the exact same sort of terminology as before. All right, so there's a few little things that are different in terms of a turbine and a compressor. So one thing is that the stator or stationary nozzle is always located before the rotor. Okay, so let's have a look why. Well, you could have it here. So here's the combustion chamber. Gases come out. As you say, you cannot let the hot gases just hit the turbine blade if they're not moving. So you have to get them moving. You have to get them moving at a high velocity first. So you must put it through a nozzle first. a nozzle or a stator, right? You put it through a nozzle or a stator to get them to spin very quickly, or to get a high velocity. Then that high velocity hits the turbine blade, and the kinetic energy is what causes the turbine blade to move. Okay, so let's say we have a stator. Or a nozzle. Let's just say and I mean, I know we have spent a lot of time focusing on sort of these angles here, right? The leading edge angle and the trailing edge angle for stators and rotors. But as well as that, especially for a stator, we must also be careful, not be careful, but be
80% ยืนยัน
very cognizant.
Sunsilk Herbal Fusion ช่วยให้ผมแข็งแรง
The stators, in other words, the area here at the inlet to the stator and the area at the outlet, right? I mean, you kind of want, it's a nozzle, so the area at the inlet is going to be bigger than the area at the outlet. I mean, I haven't drawn it terribly good here. They look the same, but in practice, the area must get smaller because you want the velocity to get bigger. Coming in, you just have the velocity coming out of the combustion chamber. Let's say V1, and then it's accelerated as it moves through this nozzle. Now, here's the thing: it's not accelerated in the axial direction. Right? So this here is the axial direction. Right, you don't make it go faster there because that's not really useful to you. That'll just make it pass through the turbine quickly, but it won't help spin the turbine. So to go back to our old terminology, like this, if the axial is the z-axis, then the perpendicular direction, this up and down is the theta direction, which is like the spinning direction, right? It's not, again, it's not the y direction in the xy axis, right? It's the theta component. It's the component in the theta direction. So here, if this is the velocity v1 coming out of the combustor, you see that it's not spinning at all. It's just purely axial. So it's just flowing in a straight line out of the combustion chamber. And when it comes out of the stator, okay, it will have hopefully a very, very big component, v theta 2. In other words, it'll still be moving in a straight line. Let's call this is CA. Here, V1 and CA are the same. All right, so it has no theta component, so it's just in the axial direction. The axial component is always called CA. That's our terminology. And at the exit, it's got an axial component CA as well. So just like the compressors, for a turbine, we will fix it so that CA is always the same, right? So the axial velocity through the turbine is constant. This is how a lot of turbines are designed. It doesn't have to be. I mean, CA doesn't, it's not like a law of nature that says, CA as it moves through the turbine stays constant. It doesn't have to. It could increase, decrease, but I think majority of turbines do design it so that CA stays constant. So what this nozzle does is that it gives the air a higher velocity V2, but it gives it a higher velocity not in the axial direction, but in the theta direction. So here, like V theta 1 is 0, and over here V theta 2 is something very, very big. So, when it comes out of that nozzle, it's moving in the axial and spinning like crazy. And then it's that spinning motion, it's that V theta 2 that hits the turbine rotor and forces it to spin, right? Forces it to to move, right? You're sort of giving it the kinetic energy of the fluid to the turbine. Okay. So let's go over here and let's look at the sort of rotor blade or one angle of the rotor blade. So all of this would be at one particular radius R. All right, if you change R, you change the velocity diagrams because you're changing the linear velocity U of the rotor. It's R omega. So omega is fixed, but as R changes, U will change. All right, so let's say I'm going to draw something like this. I don't know, something like that. This is the sort of cross-sectional profile of the rotor blade, and let's say it's moving clockwise then at speed U. All right, and here's the second blade moving clockwise at speed U. Okay, so if U is downwards, then this here would be minus U. So V minus U is W. So that vector there, that red, that would be the relative velocity of the hot gases relative to the rotor. So I've kind of drawn the rotor wrong. So let's see, it would maybe be something, I think like this. All right, pretty bad at drawing, but something like that. So W2 would hit it like that. Now, so there's a little difference here now between the turbine and the axial compressor. All right, so the difference is that it changes things a little bit, but is that V theta 2, so that's the axial component of the velocity that coming into the rotor that's spinning faster than the rotor is moving. All right, in other words, the air is moving faster than the rotor in the theta direction. The air is spinning faster than the rotor. Because it has to, right? The air is the one pushing the rotor. And you can't push somebody if you're moving slower than them, right? The air can't push it if it's not moving faster than the rotor. For the axial compressor, if you go back and look at the velocity diagrams, that wasn't the case. So the air could come in spinning a little bit, but the compressor was rotating faster than the air, and the rotating compressor was like making the air spin, was giving the air a theta component. But here, the air is giving, is pushing the turbine rotor. So V theta 2 is bigger than U. All right, and I'll call this, so over here, sorry, this is just, let's say this is point 1. So the stator and the rotor together, again, are called a stage for the turbine. Point 1 is the inlet to the stator. Point 2, the exit of the stator or the inlet to the rotor. And then point 3 is the exit of the rotor. So this angle here between the relative velocity and the horizontal there, that's called beta 2. This angle here that V2 makes with the horizontal, that would be alpha 2. So just like we had before. All right. Now then, at the exit at point 3, what's it coming in? It's coming in at V1. Okay, so we would want it to leave as V3 with no swirl, because we want V3 and V1 to be the same, just like an axial compressor. So V, let's see. This here is minus U. All of these should have like vectors on them. There, that is a W3, beta 3. And I mean, I didn't put it in, but alpha 3 is 0, right? The angle the velocity makes with the horizontal. So that would be what it looks like. And then this angle here would be beta 3 to match sort of W3. And this angle here, what's that, beta 2 kind of thing, something like that. So this is the way the rotor would be designed. Let's see. So a few things. So one is that we want CA at 1, CA at 2, and CA at 3 to be the same. So the axial component stays the same. As I said, it's the way most turbines are designed. And just at the inlet and exit of the stage, so V1 to be equal to V3. Again, for the same reason that this is done for compressors, you want the, if the velocity coming in and leaving the stage is the same, then you can design, you know, the stage that follows this. So the second stage over here can be the same as the first stage, right? You can just, the blade shape can be exactly the same. So you just have to build sort of one stage and copy it 3 times, and then you've got 3 stages then. Right? So that's for that reason, which means that well, mean that alpha 1 is equal to alpha 3. I didn't put in, you know, in most cases, the velocity out of the combustion chamber is just in a straight line. It usually doesn't have any swirl anyway. If I wanted to make it a bit more general, like I could have drawn, you know, if I wanted to V1 like this with a component V theta 1, and this is CA, and then the exit then V3 would be the same, but it's okay. It's all good. It's all good. Okay, so yeah. So basically, the kind of analysis of a gas turbine is the same as for a compressor. So what we're trying to do is look at the total energy drop of the gases. So when the gases come in, they have very high energy. Let's say here we have T total 1, right, at the exit of the combustion chamber, here we have T total 2. And at the exit of the rotor, T total 3. What's the relationship between T total 1 and T total 2? The total temperature at the inlet to the nozzle and the total temperature at the exit of the nozzle. No one? No. Right, they're equal. It's just a nozzle, so total temperature stays the same. And through the rotor then, which is bigger, T total 2 or T total 3?
T total 2.
Thank you. Right, is bigger because the gases are giving, the energy is not the same going in and out. It's less energy coming out because the gases are giving their energy to the rotor to spin the turbine. All right, so that would be let's see, that would be the relationship there. Okay, so let's just for a second look, because it'll come in handy later on. Let's just look at some trigonometry with this velocity diagram at point 2 and point 3. And let's try and match some things up if we can. So taking point 2, all right, the velocity u, the linear blade velocity u, is going to equal c a tangent alpha 2 minus CA tangent beta 2. So let's have a little look at that. It's getting a bit messy, I know, but CA, so this here is alpha 2. CA tangent alpha 2 is going to be that distance there, right, which is bigger than u, minus then CA tangent beta 2 is that distance there, CA tangent beta 2. So the big one minus the small one is equal to u. And if I look at point 3, I get u is equal to CA tangent of alpha 3 plus CA tangent of beta 3. So if you look here, this here is CA tangent of beta 3 is u, and tangent of alpha 3 in this case is 0, but it doesn't have to be in the general sense. Like I think the slides here, you see it's not 0. So here I've put I've let the velocity come in, and it has some swirl here, so it's spinning a bit as it comes in, just to make it general, right? In general, like normally alpha 1, the angle alpha 1 here is 0. It's just coming in a straight line, but let's make things a bit, generalize things if we can. So then at the exit, you'll want V3 to be the same as V1. So you'll want V3 to have a swirl component. So in that case, CA, that's that, multiplied by the tangent of alpha 3. Well, that's just V theta 3. That's that length there. And CA tangent of beta 3 is that length there. So you add the two together, and you get the magnitude of u. Okay, so That's what that is. Okay, and since U is the same at the beginning and the exit of the rotor, what you get is tangent of alpha 2 minus tangent beta 2 equals tangent of alpha 3 plus the tangent of beta 3. Or just tangent alpha 2 minus tangent alpha 3 equals tangent beta 2 plus tangent beta 3. Right, this is just from trigonometry. Okay. So let's look at the work that we get out from the turbine at this little section here, at this radius r. So the mechanical work out, or the turbine work out, is the torque from the fluid, if you will, the torque from the fluid pushing the turbine multiplied by omega. The torque from the fluid is the radius you're at, the change in angular velocity multiplied by omega. Right, so this is the specific workout. This is the workout per kilogram of fluid. And we'll use WS here, workout from the stage. So the workout, the specific workout from the stage then is R. So the change in angular velocity is V theta 2 minus R V theta 3. Right, so the air has an angular velocity coming in as R V theta 2, a very big one, and when it leaves, it has a small angular velocity, R V theta 3. So that energy has gone into the rotor. Okay, and omega R is just U, so I could write this as U V theta 2 minus V theta 3, no problem. I could also do a little bit of trigonometry and write U. So V theta 2 is CA tangent alpha 2, and V theta 3 is CA tangent alpha 3. Just write it like that. So this is equal to U multiplied by CA, and tangent alpha 2 minus tangent alpha 3, there, that's just equal to tangent of beta 2 plus tangent of beta 3. Okay, and this is the specific work out of the stage, which is also equal to CP from, so this here is the change in angular momentum of the fluid, and it's also equal to the change in energy of the fluid, if you will. T total 3. Is that right? T total 3? No, T total 1. My bad. 1 minus T total 3. Right, that's the change in energy of the fluid. Okay, so so I can write UCA tangent beta 2 plus tangent beta 3 equals CP T total 1 minus T total 3. Okay, something like that. So what we are doing here is that we're slowly building up a model for the workout from the turbine as a function of, you see here, this is the angle of the turbine blades. So if we go back up here, you see beta 2 and beta 3. Excuse me. Is the beta 2 is the rotor leading edge, and beta 3 is the rotor trailing edge. So we're relating the design of the blade the shape of the blade, excuse me, to the work output, right? So this is, or to the energy that the gas turbine gives to you. All right, so let's see what the slides say. All right, a little bit messy, but saying the same thing. You got an inlet velocity, the nozzle or the stator, it gives it a very, very high theta component. It really spins the velocity. It's spinning, the theta component here, V theta 2, is larger than U. And it pushes the turbine so that when it leaves at point 3, it's now not spinning as much because it's sort of given its kinetic energy to the turbine. Okay. What do I say here? So in the first stage, usually V1 is just axial, like it's just straight out of the combustion chamber. It's got no reason to spin. I don't think anybody, I don't think it spins at all, but I just drew it like this, just to make it general. So in a multi-stage turbine, more than one stages, then V1 and alpha 1 will be equal to V3 and alpha 3. So V1 and V3 are supposed to be the same here. Alpha 3, sometimes known as the swirl angle. So U increases with the radius, we know that. So the velocity triangles vary from the tip to the blade. So, depending on what radius you take, the velocity triangles will look a little different. So the shape of the turbine blade changes from hub to tip. All right. Since I've just calculated the specific work per unit mass. So what we'll do is we'll simplify things and we'll say, well, if we take the radius to be the midpoint, then when we calculate the specific work at the midpoint, then if I multiply that by the total mass flow rate, not just at the midpoint, over the whole gas turbine, I'll get a close answer to the work output from the whole turbine. Okay. We'll also, in this class here, we'll keep the axial velocity CA constant between the stator and the rotor. Okay, so I think we kind of did this. So the axial component is constant. So CA tangent alpha 2 minus CA. So we come up with this. We did this sort of already. This is just sort of looking at the formula for the velocity U here and a formula for the velocity U there, and putting them together give you that. So then the output work, or the output specific work, is T omega divided by the mass flow rate. So that's there, change in angular momentum of the fluid, which gives you this, which turns out to be that, which turns out to be that. So this here is important. It's the work output in terms of the angle of the rotor. Okay. So for a compressor, we had this kind of limitation that limited the relative velocity at the inlet and outlet of the rotor to being pretty close together. Because the compressor, you can't change the relative velocity too much if you try and do it, the flow then will not stick to the walls of the compressor, will not follow the shape of the blade. It will separate. You get flow separation is what it's called. Flow separation in a turbine is not really a problem because here P1 is a very, very high pressure, right? And P3, well, as you flow out the gas turbine, you're flowing into atmosphere, right? So it's just atmospheric pressure at the other end of the turbine. So the flow doesn't want to separate and doesn't want to go backwards. Like the gases in here do not want to go that way. All right. So this de Havillier limit is not really that important. Boundary layer separation doesn't really happen. Like the gases want to move the way you're pushing them, right? The way you're making it go. That's why compressors are more difficult to design and to operate, because you're trying to move a fluid in a direction it doesn't want to go. Okay, so we have two formulas for the specific work output, right? You got one here based on, I guess, Newton's second law, and one here based on the first law of thermodynamics. So they're both. So we'll line them up, or we'll make them both equal, we should say. So let's just do that. Let's just bring in the efficiency of the stage real quick. So let's take a TS diagram here. This would just be the TS diagram for one stage. Let's say here, this is T total 1. So this is the total energy at the inlet to the stage. And this is P total 1. This is P total 3. Right, so total pressure at the inlet, total pressure at the exit of the stage. And if it's an ideal stage, the temperature of the gases will drop down to T total 3 with a little s there, meaning for constant entropy, right? The entropy stays constant. Of course, that doesn't happen because there's friction in the rotor as the gases like rub against the rotor. They generate a little bit of heat, so you're going to get some entropy generated. You're going to get some heat. So in reality, the T total 3 will be a little bit hotter than T total 3s, the ideal temperature decrease. Okay. All right. So, and we can define an efficiency for the stage. We do as being T total 1, the small one, minus T total 3. So the inlet total temperature minus the actual outlet total temperature divided by T total 1 minus T total 3 ideal. So small one divided by the big one. Now I can divide above and below the line here by T total 1 and T total 1. So this is equal to, drawing it white is better, 1 minus T total 3 divided by T total 1 divided by 1 minus T total 3 ideal divided by T total 1. And since this is ideal, I can, use the isentropic relationships and substitute the pressure for this temperature ratio here. So this is equal to 1 minus T total 3 divided by T total 1 divided by 1 minus P total 3 divided by P total 1 to the power of gamma minus 1 over gamma. Okay. And yeah, that's the efficiency of the stage. All right, so the efficiency of the stage multiplied by 1 minus P total 3 divided by P total 1 to the power of gamma minus 1 over gamma. Multiply across by T total 1 equals the change in total temperature across the stage, which is just, if you will, T total 1 minus T total 3, the real. All right, so I have this formula here. Okay. And I have U CA tangent of beta 2 plus tangent of beta 3. Okay, so this is the total temperature change across the stage. If I multiply this by CP, I get the total energy change across the stage, which is equal to this. So this is equal to CP delta T total for the stage. Okay, so kind of putting it all together, UCA divided by CP tangent of beta 2 plus tangent of beta 3 equals the efficiency of the stage, T total 1 minus P total 3 over P total 1 to the power of gamma minus 1 over gamma. All right, so this here is a formula that relates the sort of pressure drop in the turbine with its efficiency and with the how fast it's spinning and what shape the blades are. So I think I've done it here. So it's just the same thing. All right, so they're all connected, if you will. The inlet energy, the pressure drop in the turbine, the blade angles, the change in angular momentum and the blade speed and how much work you get out, they're all connected together. Like you can't change the shape of the blade or the speed of the blade without changing the work output. Stuff like that. Just give me a second there so I put my notes in. All right. Sorry about that. Okay, so here's it's a question that actually I think you would have been able to do after the first 2 or 3 weeks of this course, right? But now you have so much more kind of information that I think you might find it hard to do. But like, it's one that you would have been able to do, I think, at the start, because it's just a nozzle, basically. It's just a nozzle type question. So it says here, like, take a flow from a combustion chamber into a stationary turbine nozzle. The total temperature is that, and the Mach flow coming in is 0.55, shown here. The axial velocity remains constant. So in other words, this velocity there and that velocity there, that component are the same. And the nozzle exit angle is 60 degrees. Calculate the inlet velocity. So what is V1 or CA1? In this case, they're both the same because there's no swirl. The exit Mach number, M2. The nozzle torque per unit mass flow rate if the radius is 0.35 meters. Okay. So yeah, so I mean, I think I've done it here in the slides. So maybe just we'll go through it there, but yeah, you kind of should be able to do it. So you're given this information here, the total temperature and the Mach number. So from those two pieces of information, you can get the static temperature at point 1. Knowing the static temperature at point 1, you can then work out the speed of sound at point 1. Knowing the speed of sound at point 1 and the Mach number at point 1, you can then get the velocity at point 1. So that's how we do part A. Part B, the exit Mach number. Okay, not too bad. So we know CA2 here, it's just equal to V1, right? So from trigonometry, we can get V2. So we know V2 at the exit. We know T total 2 at the exit, right? Because it's just 1800. It's equal to T total 1. It's just a nozzle, right? So T total 1, T total 2, the same. So we know T total 2, we know V2, so we can get T static 2. Knowing T static 2, that gives us then the speed of sound at point 2. Knowing the speed of sound and V2, we can get the Mach number at point 2. All right. So, as I said, I think this is all stuff you would have been able to do
ยินดีต้อนรับทุกคนเข้าสู่
within the first couple of weeks of this
ถ้า
semester.
เครื่องใครไม่มีอันนี้เดี๋ยวก็ต้องมาว่า
Okay, so to get going, you get the static temperature at point 1. It's 1,741. Then
รักพบเพียงสัปดาห์แค่ครั้งแค่รักแค่เดินผ่านมาไม่พูดจาไม่ทักไม่ทายไม่รู้ว่าใครเหตุใจจึงรักกันไม่ทางเรื่องเพราะฝันความผูกพันช่างง่ายดายรักพบมีอยู่จริงในนิยายหนังสือนิทานเพลงรักแสนหวานกับความฝันแต่วันหนึ่งฉันผ่านมาพบเธอตรงนั้นดวงใจเป็นเดือดเป็นร้อนฉันทรมานเรากับโดนมนต์แม่หมดสะกดพลันนาทีนั้นฉันรักเธอเท่านั้นรักพบเธอถึงเป็นอย่างไรเพราะเธอใช่หรือไม่ไปจากใครที่ฉันเป็นจากวันนั้นหัวใจรู้สึกเองและชัดเจนว่าทุกสิ่งเกิดขึ้นจริงใช่ฝันไปได้พบจึงเข้าใจไม่อยู่จริงท ว่าเขาเป็นใครเมื่อถึงน้ำลายไม่มีทางจะเข้าใจมันได้แต่วันนี้ฉันพามาพบเธอจุดนั้นและดวงใจเป็นเดือดเป็นร้อนซึ่งทรมานเราก็โดนมองแม่หมดสะกดพลันนาทีนั้นฉันรักเธอเท่านั้นรักแรกพบรู้เธอใจรู้ไหมจากใครที่ฉันเป็นจากวันนั้นเธอไม่ว่าใจรู้สึกเองและชัดเจนว่าทุกสิ่งเกิดขึ้นจริงใช่ฝันไปได้พบถึงเข้าใจ
Okay. Well, doesn't look like they're there. So,
แล้วมันก็ยังไม่กลับนอนเราก็นอนไม่หลับเกือบจะเวลาเช้าในคืนที่เหน็บหนาวคุยกันถึงเรื่องเก่าๆวันที่เราไม่เหลือใครเย็นมือคล้ายๆมันสั่นมองเธอแล้วใจยิ่งหวั่นกอดสักทีได้ไหมแต่ก็คงใจไว้เอาจริงๆฉันคงไม่กล้าปล่อยมันผ่านพ้นไปและช่วงเวลาไม่รู้อะไรที่มากดดันให้ฉันได้ฉันเลยในใจไม่กล้าจะเอ่ยให้ฉันได้พูดได้นานว่าฉันนั้นรักเธอก็ปากมันเผลอไปอยู่ในเวลาที่สองเราอ่อนไหวเลยตัดสินใจพูดคำว่ารักและฉันไม่รู้ตัวได้แต่ยอมรับมันเก็บคำบางคำซ่อนไว้ใจฉันนั้นรักเธอฉันเผลอออกไปมองเธอสวยไม่เบื่อคุยกันเหมือนเราเป็นเพื่อนกอดสักทีได้ไหมแต่ต้องคงใจไว้เอาจริงๆฉันคงไม่กล้าปล่อยมันผ่านพ้นไปและช่วงเวลาไม่รู้ไรที่มากดดันให้ฉันได้ฉันเลยในใจและกล้าจะเอ่ยให้ฉันได้พูดได้นานว่าฉันนั้นรักเธอก็ปากมันเผลอไปอยู่ในเวลาที่สองเราอ่อนไหวเลยตัดสินใจพูดคำว่ารักน้องและฉันไม่รู้ตัวได้แต่ยอมรับมันเก็บคำบางคำซ่อนไว้ว่าใจฉันรักเธอฉันพร้อมออกไปฉันรักเธอก็ปากมันเผลอไป ตัดสินใจพูดคำว่ารักและฉันไม่รู้ตัวได้แต่ยอมรับมันเก็บคำซ่อนไว้ว่าใจฉันนั้นรักเธอและซึ่งกับเธออีกครั้งฉันรักเธอฉันเดินออกไปครับขอบคุณมากครับเปลี่ยนพันไปไม่เหมือนก่อนเราคงมาไกลได้เท่านี้หากฉันไม่ได้อยู่ดูแลเหมือนวันก่อนช่วยบอกได้ไหมว่าเธอเข้มแข็งหากฉันไม่ได้อยู่ข้างเธอดังวันวานจริงๆตอนนั้นก็ดีจริงๆใจฉันไม่อยากเสียเธอไปแต่การเวลาใจร้ายเหลือเกินที่นำพาเธอให้ไกลจากฉันโอ้การเวลาใจร้ายเหลือเกินที่ทำให้ใจของเธอขอให้เธอได้เจอแต่คนที่แสนดีอย่าได้ไปเจอใครที่ทำร้าย